We want to take a look at solving quadratic inequalities. We're going to solve these symbolically, so we've got some algebra to do. First thing we're going to be taking a look at, we have two separate functions. The first one, x squared minus 9x plus 14 less than or equal to 0. Now, if I want to know when is this function going to be less than or equal to 0, first thing I need to know is, where does that value equal 0? So we want to know, when does x squared minus 9x plus 14 absolutely equal 0? Now this happens to be factorable. X times x for the x squared, 7 times 2 for the 14, making them both negative so that they add up to a negative 9. Since I know only something times 0 is equal to 0, then I know that x minus 7 is equal to 0, or x minus 2 is equal to 0. And we can solve each of these resulting equations individually. Adding 7 to both sides of my first equation, we get that x is equal to 7. Adding 2 to both sides of my second equation, we get that x is equal to 2. Keep in mind, all we figured out so far is when does the function value absolutely equal 0. But the fact is, I have different regions that we need to take a look at. What we've done is separate our number line for x in 3 portions. I know for a fact 2 makes the equation equal to 0, and I know that 7 makes the equation equal to 0. So when I take a look at the values of x, we're going to have 3 regions to consider. The first region goes from negative infinity all the way to the number 2. We know it's not equal to 0. What we haven't figured out yet is whether it's greater than 0 or indeed less than 0. Our second region goes from 2 to 7. That's the values in between where we know they equal 0. And our third region would start at 7 and go on to infinity. So we have 3 regions. We're going to have to test 3 values. In our first region, call him region 1, I can take a look at, well, 0 is definitely a number to the left of 2. In our second region, I need a number between 2 and 7. Well, I'm just going to test the number 3. Our last region, region 3, we want a number from 7 to infinity. I'll just pick a number. Let's try the number 10. These values we can now test by putting them into our function. So our first value, when x was equal to 0, we would have 0 squared minus 9 times 0 plus 14. Well, this is actually going to be equal to 14. 14 is bigger than 0. So I know I am not interested in region 1. My second value, let's test the number 3, which means we would have 3 squared minus 9 times 3 plus 14. So this is going to give me 9 minus 27 plus 14. That's going to give me a value of negative 4. Which is nice because I know that that's a value that is strictly less than 0. So region 1, we saw was positive, greater than 0. Our second region, region 2, was definitely less than 0. Testing that third value in region 3, let's try the number 10. We're going to have 10 squared minus 9 times 10 plus 14, which is 100, minus 90 plus 14. That's going to give me a positive value. Positive 24, he's definitely bigger than 0. So I am not interested in the first region. I'm not interested in the third region. We have our solution. Our solution is all the numbers starting at 2 and going to the number 7. Our first region, when we plugged in a value, was strictly positive. Our second region, when we put in a value was strictly negative. Our third region, when we put in a value, gave us something positive. Looking at our inequality, we want to know when was it less than or equal to. So because of the equality, we only need to make one change. Turns out instead of having these parentheses, because the function value can be equal to 0 also, we would include the number 2. We would now have a bracket. We would also include the number 7. We would also have a bracket here. Please do not confuse. The original regions all had parentheses because we knew at 2 and at 7 is where the function value was exactly equal to 0. And this should make sense. After all, x squared minus 9x plus 14 is a parabola that opens upwards. And so if a piece of it is below 0, I would have expected it to be some piece that was bounded between two numbers. So it's reasonable that we start at one value and end at another value. All right. For our second inequality, we have a negative 2x squared plus x plus 10 is less than 0. Really don't like having a negative coefficient for x squared, so I'm just going to go ahead and factor out a negative 1 at the very beginning. I would have negative 1 times 2x squared minus x minus 10. This is still less than 0. We can factor this quadratic, 2x times x for the 2x squared, negative 5 and a positive 2 for the negative 10, and checking negative 5x plus 4x will definitely give me that negative 1x. I like the way he looks. And from here we get two solutions because 2x minus 5 could be equal to 0, or x plus 2 could be equal to 0. Solving each of these equations independently, I would have that 2x is equal to 5. Dividing by 2, I get a fractional answer, nothing I can't handle, 5 halves. Our second equation, I can subtract 2 from both sides, so we would have that x is equal to negative 2. I get my second solution. But again, we're looking at specific regions. On my number line, one solution was negative 2, a second solution was 5 halves, and again we can choose test points for each of these three regions. The first region goes from negative infinity to negative 2, the second region from negative 2 to 5 halves, and our third region from 5 halves on out to infinity. A number smaller than negative 2. Well, we can test negative 3. Why not? A number between negative 2 and 5 halves, my favorite number to put in, 0. And a number that's bigger than 5 halves, but 5 halves is 2.5, so 3 is a sufficient number to plug in. And so when we evaluate, and I'll leave this for you, plugging the number negative 3 into our function is going to give me a negative value. Plugging the number 0 into our original function would give us a positive value, specifically positive 10. And plugging the number 3 into our function and evaluating will give us a negative value. Well, I think now we're ready to solve when is this function going to be less than 0. And the function is less than 0 whenever our function values were negative. Region 1, region 2 gave us positive values. Region 3 also gave us negative values. So our solution here, we will have the region from negative infinity to negative 2, or the region from 5 halves to positive infinity. And this should also make sense. After all, this was originally a parabola that opened downwards. So if a parabola opens downwards, I would expect the part that's less than 0 to be those two tails, which we have found. The part less than negative 2 from negative infinity to 2, and the part from 5 halves on to infinity. I like the look of that answer.